we have a problem here which asks us to find all positive integers n such that this expression is divisible by 169, if any exist. So we don't even know if any such integers n exist yet. I guess it's up to us to determine. So how can we start? Well, some of you might instantly notice that 169, this number is just equal to 13 squared. It's the square of a prime number. And this might look very useful, because if this is divisible by 169, then it must be divisible by 13. So perhaps we can first consider this number in mod 13. So let's try that. If we do 12 to the n plus n in mod 13, then what will this be congruent to? Well, in modular arithmetics, you can actually mod the base of any exponential expression. So you see this 12 to the n over here, you can subtract this 12 or add this 12 with any multiple of 13. So in this case, we can subtract 12 by 13. So this will become 12 minus 13 to the n plus n. And obviously, okay, it's congruent in mod 13, right? And well, this expression is just equal to negative 1 to the n plus n mod 13. Okay, this looks a lot more simpler because we have negative 1 to the n, and maybe we can consider whether if n is even or odd. But to be honest, other than trying some small values for n, and then hopefully determining a pattern, if there is any, there's really not much to do. I mean, even if you do solve this congruence, you'll be getting it in mod 13. But we want mod 169, so you're going to have to somehow make that jump. Therefore, we might want to restart and seek another path. Okay, we're back with a blank board, except for this, because this is actually going to be pretty useful. So how can we maybe rewrite this expression so that we can work with mod 13 squared more effectively? Well, consider this. We have 12 to the n, right? And we can write 12 as 13 minus 1 to the n. And notice that we have an exponent of n on the top, and n is a positive integer. And we also have a binomial inside here. Well, we can use the binomial theorem to expand this, right? Now, what's so good about that? Check this out. Okay, after expanding, this might look like a complete mess, but this actually works out very nicely in mod 13 squared. Notice the terms from n choose n to n choose 2. So all the terms that I'm underlining in red. Notice that they have 13 squared and 13 to the power of something that is definitely greater than 2, right? Given that n is sufficiently large. So basically, all of these have a factor of 13 squared. Therefore, everything that I've underlined in red is basically congruent to 0 mod 13 squared. So therefore, this entire expression is congruent to, okay, everything in red is 0, and then this over here is just 13 times n, times negative 1 to the n minus 1, and then plus, and choose 0, that's 1, and then we just have negative 1 to the n. And this looks much, much better. In fact, this is in mod 169, mod 13 squared. So this is going to be very convenient. And of course, we can simplify this. We don't need the 0, right? Now, let's not forget that our original expression was 12 to the n plus n. So let's not forget about that plus n. So we're going to add n on all sides of the congruence, just to make sure that we're working with the correct expression. Okay, so now we have something here at the bottom, and this we can very much deal with, because we just have negative 1 to some powers, right? We can just deal with the cases when n is even and when n is odd. So we'll consider our case 1, when n is even. Well, in this case, we have n minus 1 to be odd, and n is even, so this expression just becomes n minus 13n, and then plus 1. And remember, we want to see when this is divisible by 169. Since this is congruent to this, then we'll set this to be congruent to 0, mod 169. And now we can rearrange this congruence, simplify it into 12n is congruent to 1, mod 169. and now we need to isolate for n. But saying that n is congruent to 1 over 12 does not make much sense. But thankfully, we can subtract this side by 169, giving us that this is congruent to negative 168. Mod 169, of course. So what is the magic of 168? Well, it's divisible by 12. So when we divide both sides by 12, we'll get an integer on this side. So if you do that, you would get that n is congruent to negative 14 mod 169. Now, we do not particularly like negative residues for our solutions, so we're going to add to this side 169. So this will be congruent to negative 14 plus 169, that's 155. And mod 169. So we have our solutions, right? N is congruent to 155. Not so fast, because remember, this solution was derived under the case that n is even. Not all integers n satisfying this will be even. So we need to further investigate. Notice that this is saying that n is equal to 169k plus 155, where k is any integer. Well, in this case, if k is going to be even, then this is going to be odd, right? That's not good. So we need to have k to be odd. If k is odd, then this will indeed be even. So therefore, we need to have n is equal to this, where k is odd. So this will be the complete solution for when n is even. However, we have one more case to deal with, and that is, of course, case number 2. We're just going to number it. And obviously, it's when n is odd. And when n is odd, then n minus 1 is even, so this expression just becomes n plus 13n minus 1. And we're going to set this congruent to 0, mod 169. And we can rearrange this into 14n is congruent to 1, mod 169. And once again, if you were to subtract 1 by 169, it actually works out nicely. So if you subtract, you get congruent to negative 168. And 168 is divisible by 14. So if you divide both sides by 14, you get n is congruent to negative 12 mod 169. And of course, we don't like negative residues, so we're just going to add this with 169, giving us congruent to 157 mod 169. And we have a solution, but be careful once again, because this is under the case when n is odd. But first, let's write out what this congruence is telling us. This congruence is telling us that I have no space. This congruence is telling us that n is equal to 169, right? So 169j, and then plus the residue, 157, where j is some integer. But remember, since n must be odd, then you can see that you must have j to be even. So j must be even. And this is another set of solutions. So therefore, we have derived all possible solutions for which this number is divisible by 169. And that's it. Throughout this problem, I hope you've come to see that the binomial theorem is actually pretty useful when dealing with exponents in number theory. And that's because they allow you to bring the exponent down into some actually, manageable expression. In modular arithmetics, you cannot just mod the exponent. That's what makes it really annoying. So the binomial theorem provides a way to bring it down to some regular expression. So yeah, I hope you learned something new from this video. If you found it interesting, then please do consider dropping a like and subscribing. Thank you very much. Bye.